Before we begin a new subject, small supplement to last week to the PCB testing. That's something missing here in our magic circle, because all the other circles were already were already discussed. So what is missing is just the testing. And in case of testing here, I mean testing of the PCB itself without switching it on, or in other words, without supplying it. This testing, so it's not electrical testing, but the rather optical one, because this is the first way. Then the testing is done. Normally, both when we are making our amateur, I would say, PCBs, and as well, this is the first mean of testing, of checking the board when we are done in factories. So testing it optically. Optical testing quite often, so sometimes is done through some automatic tools. Especially now with the artificial intelligence and high resolution cameras that we have all around us, but still very strong here is a good woman, is a good human, skilled person with decent microscope or special type of microscopes, because for the testing the special microscopes are quite often in use. And what is being looked for and what can be found after the assembly, especially the assembly in the oven, after the soldering of the PCB board. A few slides about it. So the view that we should see, that of course two-dimensional view, you can see on the slide. So solder with no bridges should look more or less like you can see here, with the also the flux visible here, because this is actually the flux itself, and of course the solder with some pad with pins. That's what's the view that we should see. Then possible problems that can be that are visible from time to time, shouldn't, but visible. For example, bridges. Take a look at the small points here, and here it means that not all solder melted together, and it does mean that the profile was wrong. Probably the soaking was too short, or the reflow was too short itself, and not all spheroids melted down during the process in the oven, so it led to those bridges. So first possible problem are the bridges. If we look at a different component, or for manual assembly, the view, so seen slightly in the 2 plus D view, the profile, a proper soldering should look like this, and then we come back to wrong profile problem. The problem, so here the bridges are that we are almost good with the profile. Here the problem is much deeper. Then it does mean that the profile was completely too short, or the temperatures were far too low set in the profile, and the spheroids did not melt down. So it's clearly visible that the paste hasn't melted, that the flux evaporated, but the spheres didn't melt together, and of course the PCB assembled in this way has to be reworked completely. So the improper profile example. Another problem with improper profile is the self-alignment problem. So self-alignment does also mean that the profile was almost good this time, but almost. So here the self-alignment is very large. Take a look. Here is the PCB. Here is the pad of the IC, and here is the paste with the soldering with the solder on top. So here the alignment is so there is no alignment. It's completely improper, the alignment in this position. So we are completely off the pad. Here the alignment is also not perfect, because we have the pad is not in the center. Within good profile, we mentioned about it previously. Within good profile, the elements are to be in the center of the pad because of the surface strength of the liquefied solder. This surface strength, this surface force will in the proper conditions, when the temperature profile is proper, then it positions the elements very accurately. I'd say it positions the elements very accurately. Here the positioning isn't perfect. So here the positioning isn't perfect. It's visible on the right photo. On the left photo, we are completely off the position. So the profile was very wrong here. Because also I can see that the surface of the solder isn't smooth, and it should be smooth. So it does also mean that the profile that we didn't heat enough. The board wasn't heated enough, or the chosen temperatures were too small. In case of THT as well, the problems may arise. Of course, we are soldering it in a bit different way, because we are using a wave to do this. But still, the problem may be, or the errors may appear, like here, that we have the solder which is not melted at all, and then the pins are not soldered with it, so they are not soaked with the solder. It fell. In fact, here is same. So we have as well. It's visible that there is a lot of flux around, but no solder visible, which means that was too few solder or too low temperature, so wrong process was chosen. Then we may have situations, so again, similar to incorrect soldering situations, incorrect view. Again, the shape is wrong, definitely wrong. Besides, we've got a lot of solder paste here, or solder on top of the pins. Here on this example, the problem comes with too much solder here used. The shape is not correct. So the correct shape, requires means a different shape here, concave and not convex, like we can see. So the shape should be like this one. So here is as well. This is as well incorrect. Means that the process was chosen incorrectly. And then with too much solder, of course, short circuits may happen. So like this one, that we have too much solder and two components were connected with the solder, which should not be the case. Then another set of problems for the BGA and LGA tape cases. So the cases with the pads underneath. So we have, if you can't see, this is the chip, and here is a PCB. So this is the PCB part, and this is the chip, and of course here are the bolts itself. We are when we are assembling the BGA, especially the BGA, then the BGA have the balls of tin on connected to the pads. We are then adding the solder paste with the printer, and then we put everything, position everything onto each other, usually using some microscope or some machine, and then we put this to the oven. So in the proper situation, we should have more or less something like seen here, more or less. So this is the still incorrect view because this distance is too high, but it's almost good. This is actually almost a proper view. But in the BGA, if for example the temperature isn't right, then we end up with this. So that this means that the temperature, so the wetting wasn't good enough, and the melting isn't complete. So the solder paste and the ball of tin on the BGA pad did not solder together. Here on the other side, too much soldering paste, and then two pads melted together and made the short circuit. So this is the very bad thing about the BGA, because in case of BGA, you see the problem is that if the soldering is improper, even one or two pads have not are differing from all the other one around, then there is a large chance there will be some problem inside. These are technical details, but generally the BGA, I like BGA cases personally very much, but it took me some time to solder it and to be able to monitor proper soldering. For the beginners, the BGAs are very difficult because, you know, in BGA cases we have pads hidden. We can't see them. So without X-ray microscope, which is very expensive, you won't be able to check inside. So you have to extrapolate the results seen from the sides to the inside. So if there is any problem like this one or this one or this one at the side, it does mean most probably that you have to rework the whole BGA chip or LGA, because these are similar cases. Similar technique is used for the PCB assembly. Another problems with too much solder visible on the board are the parts of tin spread around the board, under the chips or around the chips, or floating somewhere as a remnants all over the chip. So generally, take a look. We can see as well here the problem. So too much solder is of course harmful, as we may get some short circuit, unwanted short circuit somewhere on our board, or the worst is the short circuit under a chip, which is usually quite difficult quite difficult for detection, and usually ends up in the need to throw the board out and take the new one, which is expensive. From much less important things, small elements like whiskers, but these are only for very professional case important, and normally we don't care because they are too small, so that we basically bother. So these are a few words about it, and to sum it up about the construction, about to sum up the subject about the PCB. For the sake of the PCB design, we are using today the EDA tools, which we use for simulation first of our device, then we are drawing schematic out of it. After the schematic, we make the routing, and then we make the fabrication files. So the fabrication, like those Gerber files mentioned, Gerber or drill files mentioned last week, but also the files for that can be printed for manual, I would say manual assembly. Because we can print each layer separately, there we can send it directly to the printer. And as well, from this kind of softwares, we've got so-called bill of materials. So that's also if you have it. I don't know if Mr. Wojcik does it with you, or did he show it to you? Did he show it to you? But there is, if not, ask him to do this, or try to localize it by yourself. Bill of materials, also a summary of all the elements, quite important during the assembly and testing phase, and during the, of course, buying phase, because we have to get the component before we start assembling our board. So bill of materials also automatically generated today. We have also a chance, if you visit the pages of the main dealers of components, like Farnell or Mauser, then they do accept the BOM files, the web pages. So you can then directly take the BOM file generated by the EDA software of your choice, and upload it to the web page, and then as a feedback you'll receive the basket with all the components from the BOM, at least the components that could be found by the in the warehouse of the particular dealer or distributor. Good. The next part. In the next part, let's move towards where's the lecture? Towards the thermal management, because that's our plan. Let me share the screen. So in our next part of our lecture, next part of our circle, magic circle, thermal management, and then cases, connectors, and the testing. But this time the testing will be about the testing of the complete devices, and not the testing about the PCBs. So hardware thermal management. That's the next part of our construction. So what about the thermal management of the devices? Why do we need to bother? Actually, the power loss of the electronic devices may be quite high. First limitation we have, first that comes to my mind at least, is the glass temperature of the PCB. So if our PCB survives soldering in the oven, which might be problematic, as mentioned last time, then still we may end up with a situation where the chip so the elements of the PCB will heat up the board, damaging it. So we'll heat it up beyond the glass temperature, the DG. Why may it happen? Why is it? In what situations can we expect it? In many situations, unfortunately, in real life, especially it is especially problematic when we intend on driving high currents and high power loads. For example, if we want to drive a transistor with a transistor, if we want to drive, for example, some kind of a motor. The motor, in order to work, to give you some examples about the numbers we are talking about, the motor usually the motors require, in order to have any substantial or useful torque, the motor require a few watts, which can be, let's put it very mildly, let's say that we do require 5 watts for rotating. That's really tiny. But then if we require 5 watt, then let's say from 5 volts, 1 amp would be necessary to flow. But then if we try to use the, if we try to make such a simple, because let's say this is a DC motor, so the circuit might be very simple with NPN transistor, let's say, because the DC motor to start to make it rotating, it's enough to connect positive voltage or negative voltage, because then the change of direction can be done, to the coils inside the motor. And so the simplest way is, of course, to do such a circuit, that we have a transistor and we just switch it on by applying some voltage here by the emitter, and if we switch it on, then the current is flowing. Let's say this 1 amp is flowing here. Yeah, but then the problem starts. Where is the problem? This voltage drop on this transistor. This is a bipolar NPN transistor. So the voltage drop is called the saturation voltage, and the saturation voltage is 0.2 volts, circa about, because it's more or less this value. Of course, what does it mean? It means that with 1 amp, the power loss on the transistor, the minimum power loss is 0.2 watt. 0.2 watt, of course, doesn't look so very scary, but that's just 1 amp. If the motor would require 5 amps, which still isn't something very, which still isn't a high number, then the power loss would get into 1 watt. And okay, 1 watt, let's say that we have 1 watt at 5 amps. Yeah, so then there should be a question from your side. Okay, what is 1 watt? We have a kettle. Each one of you probably have a kettle in the kitchen. And the kettle is usually 2 kilowatts, right? Or 1.5 or 2.2 kilowatts. So what is 1 watt? Yeah, for boiling water, 1 watt is pretty nothing. But of course, for the small electronic devices, and especially the small silicon we have inside, because normally in case of transistors or elements, various kinds of elements, the area of the silicon die, which is inside, the area is like 1 millimeter square. That's the common area. Sometimes it's more, sometimes it's less, but quite often it's just about roughly 1 millimeter square. So 1 watt per 1 millimeter square is very high power density, actually. And normally this without proper heat transfer from such a silicon, from the silicon to the ambient, with proper heat transfer techniques, such a silicon may evaporate. So 1 watt is really a lot. It's really a lot. It's requiring really good power dissipation from the chip. For example, this is the case of the SO 2, 4, 6, 8, 10, 12. This is kind of SO24 case. 1 watt in this case would melt the chip down, frankly. So 1 watt dissipation. So this case is absolutely not suitable because of too high thermal resistance. And 1 watt power dissipation, if there is here, if we would apply it for this case, for this classic SSOP or SO24, would damage the electronic inside. So that's the problem. In case of heat dissipation, there are a couple of techniques for dissipating heat from a couple of ways of dissipating the heat from our chip. element. The simplest technique is to, of course, we have the dissipation by convection, by conducting, because the heat is conducted, the heat is dissipated, and the heat is radiated, because they are, from physical point of view, they are three main techniques, three main not techniques, but phenomena behind the heat transfer. But putting it aside for a moment, there are three major paths for radiating, for transferring the heat out of our silicon. The first is to the dissipation to the ambient, direct dissipation to the ambient, through radiation or conduction, so that we have the silicon, then there is some case, and then the heat is dissipated. This way is the standard one for any component, but the problem is that this part is not always conducting well. Therefore, second door is to reduce the not well defined or not optimal resistance, thermal resistance of this part of the shield of the case, and to connect the silicon to the ambient directly via thermally conducting materials, and that's the so-called radiator, the use of radiator. This radiator, then we can connect also sometimes, because here is a dedicated radiator, sometimes, and this is the part, the road number 3, is to use this the pads. The problem with using pads, unfortunately, is that the connection here, usually we talked about COB boards, and those COB boards are, as mentioned, usually they're very thin golden wire is being used here, and the very thin golden wire, it's conducting heat quite good, but it's very thin, which does mean that the electrically the pad and the silicon are connected, but thermally this connection isn't the best. Unless a special construction is done, and instead of a thin thin golden wire, there is a wider aluminum bar used for connecting, but that's expensive and used only for very special ICs or for transistors. So normally in integrated circuits, the method number 3 can be neglected. The amount of heat transfer, usually the transfer through some thermal path, we call it a thermal path. Here is a power path, but actually it's thermal path. That's the normal name. Are used for transferring the heat out of, effectively pumping the heat out of the structure. Then the thermal path can be used in 2 ways, depending if the thermal path is close to the PCB or flipped to the top, because in this case it is pointing downwards, it is pointing to the PCB, but also it can be pointed upwards. For if the thermal path is up, then we can connect here some radiator. We'll talk about the radiators and their tapes during today's lecture. Also with some fans, so with forced air movement. Then if it is pointing downwards, then we can connect it to then we can design a PCB. Then we can design the PCB in a special way in order to to dissipate the heat properly. Anyway, so all those things I'll try to issue during the lecture itself, during today's lecture, during this hour and the next one. So we have to actually do the thermal management, because we talked here about the thermal management, but of just one case. But of course, we have to do the thermal management at the device, the board, and the box levels, because normally our device, when we are designing an electronic device, we are designing a complete package with the case, and we have to think about the thermal management, not only about our PCB. So this is the board, the PCB board, but also we have to think about the box level. So, for example, how to dissipate the heat from the box, from our board outside. That again might be problematic. Might be problematic because and might limit the case, the materials of the case, that might limit the shape of the case, because take a look, if the board we design is not heating up, so basically there is the power consumption of the board usually roughly lies within a watt or below, then usually for such cases the boxes that we put our device into can be of any shape, of any size, and any material can be used. Even can place the PCB board in a wooden box, because wood is very good insulator here. So for 1 watt or below, even the wooden box could be used. But for if power loss on our board, total power loss exceeds 1 watt, practically, and goes towards single watts or tens of watts, then we have to either design a radiator, or the box has to be made out of aluminium, out of steel, out of copper sometimes. So it really depends on the application. It really depends on the application itself. The problem really arises or comes from the fact that we'll analyze in a moment, in a more deeper way, than the possibility of dissipation, which is actually shown here on the board of a device, diminishes with the increase of the temperature. Of course, this is the free air temperature, so you might ask, okay, where do we have 80 degrees? So nowhere, because it's not even in Saudi Arabia there we have 80 degrees as the free air temperature. And I would agree, but the problem is that when, for example, let's consider the case that you put a device in a wooden box. So there is a box, let's say it's wooden. Of course, with a lid on top, again wooden, and we have a PCB board here, and the PCB is dissipating some heat. So let's say that we are dissipating 1 watt. Okay, so in the beginning there is a 1 watt dissipation. So let's say that we have a 0 degree here inside the temperature, with the temperature sensor placed here. So we have a 0 degree. So then, of course, we can dissipate 3.5 watt, not a problem, and we are dissipating just 1 watt. But because there is the box is made from insulating material, this 1 watt, from this 1 watt generated by the PCB device, let's say that through a good insulation, because of the good insulation, only 0.1 watt gets out. And the other 0.9 watt is increasing the temperature. So from 0, our temperature is going up, and really may end up with, let's say, 90 degrees or 100 degrees inside, which would then even further reduce the dissipation capability and damage something. So something may burn, may explode. And for sure, the reliability of our device will decrease, because the higher the temperature of the PCB, the lower the lifetime of the whole device is. We'll talk about it near the end of the semester. So generally, we have to think about the thermal management, first of all, at the device level. So by choosing the proper package with heat sinking, so all the devices, all the transistors, integrated circuits with that are to dissipate heat, they have to have. We need to choose the proper package for them. On the market, so stopping here, on the market, we have quite often an option that the same device is available in various cases. So we have smaller cases, larger cases, cases with thermal pad, cases without thermal pad. We've got plenty of choices quite often. So sometimes we have 2, sometimes even 5, 6, 7 different cases for the same silicon. The reason for this is, of course, first of all, that various scales of integration. Some people need the device to be very small. Some the other one, they would like to see the chip without a microscope, and therefore have the larger case. But the second reason for various packages is that for some applications we don't need thermal pad, and for the other one, yes, we do. And some small example, some very small example. When we are making a power supply circuit, quite often we're using a 78XX family of chips, of linear regulators. It can be 7833, for example, for generating here the 3.3 volts. So then we have here at the input something like from 5 to 15 volts, let's say, non-regulated, and the output is regulated. And that's really fine. The problem is that for some applications, the current here would be like 0.01 amp. While for the other applications, we may need a current of 1 amp. And let's consider the current of those two cases. So small current consumption, large current consumption. What would happen? Let's consider, for simplicity, that the input voltage would be 13.3 volts to make it easy for calculation. So something in this range, but let's say that it's 13.3. So what does it mean? It means that for the voltage drop here would be 10 volts, would be 10 volts here, because it's 13.3 minus 3.3. So the voltage drop on the on this regulator. So at 0.01 amp, 10 times 0.01 means that the power loss here 0.1 watt in the first case. But the power loss in the second case, as you can easily calculate, would be 10 watt. 10 watts. 10 watts is a very high power loss. For electronic component, requires the heat dissipation usually on the large radiator, or with forced airflow, or even with a liquid. 10 watt, horrible power. And still take a look. So for this application, for the first one, for the first application, so for this one, we can use small case. While for this application, definitely a case, a board, a package with special sink, with special thermal pad must be used. So that's what is meant here by proper package with heat sinking. Of course, then thermal vias with to sew planes in order to force to dissipate as much heat as possible to the PCB. Then might be necessary to add the airflow unobstructed. So it means that we can't have a lead on our device over our PCB, like is shown schematically on this picture. And then if we have a solder part, then we should solder it, the thermal part itself, we should solder it to the PCB. At the board level, because this is about the device level, at the board level, we need very often to generate the heat flow out of the board. So here is an unobstructed airflow against one component, but at the board level, we should think, for example, where to mount the PCB, or how to mount it, where to place the components that take the most, dissipate the most of the heat. So to make the proper airflowing as well. So then we should think about, for example, should we use the heat sinks, and so on and so on. And then on the box level, then we should think about, on the box level here, because it's not something different, but at the box level, then we should think, first of all, how to dissipate the heat out of the device. Should we use some special fans? Should we use should the case be out of thermal conductive material? And this kind of stuff. Okay, before we go into greater details about the construction of electronic devices, about the tapes of the airflow and how much the airflow is influencing the possibilities, or the possibilities of heat dissipation, first we have to get down to the physical model. But before, there is a break. But because there is a break right now, so in a minute, and this is a bit more to tell than just for a minute, then let's make a pause here, and we'll get back to the model of the heat transfer within any electronic device, or within any device, because the model, as you will see, is universal. So let's put a comma here, and we'll get back to this after a 15-minute break. Okay, we're back. So the model for further operation, we need to understand the model. The thermal the thermal flow, or the heat flow maybe, is normally modeled by so-called thermal resistance. The thermal resistance, which is sometimes, it depends. So it's sometimes marked by theta, sometimes by simply RTH. Here it is on this slide. It's theta, but RTH is as well used throughout this presentation. Generally, the power dissipated from an object is proportional to the difference in the temperature between the object and the ambient surrounding, and inversely proportional to so-called thermal resistance between the object and the ambient. So for the scale, or for the power dissipation values that we meet in the industry, in the electronic industry, and for the temperatures we have in the industry, this formula, this model, the simple model, is very true. Is very much true. So we don't need to use any matrices, integrals, and other complex formulas. So just simple formula that the power is a ratio of the temperature difference against the resistance between the objects. Here is the formula is for the junction and the ambient, which means that the junction is this, because it's of course on the picture. So this is this node on the picture. This is the silicon itself, the silicon die, But on the path between the junction and the ambient, we've got usually couple of elements, that we have to include quite often into our calculation. Like, for example, the first and simplest and quite often used is the case itself. So in the first simplification or the second simplification, we are including in our calculation case, which means that we have the situations where there is a junction, and the junction goes to the first of all goes to the heat goes to the it goes to the ambient, so that we've got according to those marking theta Ca, theta Jc and theta Ca. So this is theta Jc, and that's theta Ch, so case ambient. Altogether, this forms as the theta junction ambient. So the total value of the resistance, thermal resistance between the junction and the ambient. If our case has a thermal pad, then we've got also second resistance to the PCB board. So it is theta junction to board, so theta J, theta JB. As mentioned, sometimes we have a theta. Sometimes the theta JA can be found in the literature under the abbreviation of RTH JA, junction ambient. Sometimes 4 letters are used, so RTHJA. So it really depends. The reason for using R and not theta is that we model again. That's very simple. For the temperature ranges we talk about and the powers that we talk about, then it's enough for us to model the resistance itself, to model the heat transfer by thermal conductance of an element of a material, and the inverse of thermal conductance is thermal resistance. Therefore, the symbol of resistor used here, and as well the R for marking, as a marking of this thermal resistance. In case of the thermal heat transfer, there are many more analogs than just the resistance, and a table summarizing the analogs between the electrical elements, electrical components, and the components of thermal modeling, used for thermal modeling, you can find here on the slide. So the current source from electrical as an electrical element, as electrical symbol, is a heat source in watts on the thermal side. The voltage source on the other side is the temperature of the ambient. Is the temperature of the ambient, or is the temperature anywhere else? So, for example, then we have the resistance. Which is electrically calculated in ohms, while thermal resistance, so theta TH or theta JA or RTH, the units for the resistance, thermal resistance, are completely different because we have a Kelvin per watt or Celsius per watt. We can also model the capacitance of the model with the capacitance CT in joules per Kelvin or in joules per Celsius. Frankly, the capacitance is modeled, or the modeling of capacitance is used to include in the calculation how much material is around and how fast the material will absorb the heat. How much heat can it absorb in another way? So, for example, this wooden box mentioned some time ago, here. I mentioned about the wooden box. Of course, the thinner the wooden box be, the lower, of course, higher thermal conductivity. And then the thicker it would be, the thicker walls it will have, the stronger construction, then the lower would be the heat transfer possible, and the higher would be the thermal capacitance. So, for example, if we have a chip like this one, then we can draw a model with the use of electrical components, electrical symbols. So we have a power source like 1 watt, let's say. Then we've got a chain of resistors. So, for example, it will be a theta junction case and theta case ambient. And then we've got the voltage source being actually the temperature of T ambient. Very simple model, yet giving us a chance to check the temperatures and showing us where we can make the improvements, or what we can model, what we can change. From practical side, we are actually, of course, we can modify the dissipated power by changing the, for example, the load, by changing the power supply voltage. We can modify the theta junction case to ambient in the real conditions by applying some heat transfer elements like Peltier module or thermal cooling, liquid cooling, applying liquid cooling there. We can, of course, change the TA by changing the box temperature. So, for example, we can place a box in the liquid nitrogen, and the TA would be minus 70 Celsius, for example, or something like this. So, on some elements, we have from this simple model, 3 elements we can modify. Usually, we can't modify theta JC. The theta JC is delivered to us by the manufacturer, depending how they did it, how they did the device, and how they implemented it in the case. The cases itself, yeah, here it is. Here you can see the differences, or the values that you can expect of this theta JC, JA even, because this junction. For the cases without any radiators and external radiators, between different common cases of the electronic devices. So the worst here that you can expect is a very popular SOIC 8 case. This is 8-pin case. That, for example, the aforementioned 7833 is available in, because the 7833 is, or 7805 for 5-volt regulation is available in this case quite often. And take a look. Here it's the thermal resistance of this case, 216 on 1-layer board, on 2-layer board. It's a 4-layer board, single layer is 16 on 4-layer board. We can expect 108, so slightly better. But even taking the better value, what does it mean, the 108? To give you the numbers, we were talking a bit before about we're taking 2 cases into consideration. One where the power loss was 0.1 watt. In the second one, the power loss was 10 watt. Okay, and take a look. The taking this formula, actually, because that's the formula, the junction equals to temperature at the top of the case times the power loss plus the power loss times the junction VJT. So actually is here, excuse me, there should be theta junction to ambient. So thermal resistance times the power loss plus the temperature at the top, so the ambient temperature, and then it would end up with the temperature of the junction. So let's then make short calculations. Let's consider that T ambient, that the ambient temperature T ambient is 20 Celsius, so standard one. And if there is a 100, so 100 we have to multiply by 0.1. This makes 10.8 plus 20, so the temperature of the junction here in this case is 30.8 Celsius. Still quite nice. But what would happen if we would like to make a power loss of 10 watt? So 10 times 100, it's 1000. So it's 1 K Celsius, if we can use such a unit. Of course, it's absolutely out of question. It's absolutely out of question. This would melt down very soon. So even 1 watt, applying 1 watt to this case would melt down the junction because the junction can survive 130, 50 degrees, something like this, and beyond this, the semiconductor inside loses its properties. So actually, 108 a standard value, and this is for quad layer board. For single layer board, it's even worse. It's 216. These are very high values that are real, and it does mean that we really have to be very careful about the power loss. In case of for other cases, the situation is a bit better, but those cases are much larger, mind that, because those cases are, so here we have a through-hole cases, so deep 20 to deep 24, but they are much larger than SOIC. Therefore, the power dissipation from those cases or expected with these cases is significantly higher. The quad flat packs, yeah, quite large. So we have a very nice 20 about Kelvin per watt, but for QFP being big 208 plus a heatsink. So take a look, there is a heatsink, but even with a heatsink, we still stay at the level of 15 or 20 Kelvin per watt, which would mean, of course, that 1 watt dissipated in the silicon would heat up the silicon cell by 20 degrees above the ambient. So with the ambient being 20, it's 40, but with the ambient being 50, the junction would have 70 grades. And of course, that's just 1 watt. 1 watt for example, microcontroller, because this is 200 cases QFP, so programmable logic. Logics are in such cases, microcontrollers are in such cases, memories sometimes. So they sometimes need more than 1 watt, leading to possible problems. Anyway, these are the values that you can expect of the thermal resistance. One more thing about the thermal management, you can find on the market in case of microcontrollers and other integrated circuits, you can find the devices dedicated to operate in different temperature ranges. A standard temperature range that you can expect is 0 to 70 degrees Celsius of the ambient. So again, the 70 Celsius doesn't come from the fact that there will be our devices to work on the desert and there will be 70 degrees, because it's not the record temperature from Death Valley is like 50 something, 56 I think, but it's of course because the ambient here is the temperature within the case. So if our box is not properly designed, in the case of the electronic systems properly designed, and we can really easily exceed this 70 degrees. And then we've got various industrial temperature range and military temperature range, which are a bit higher. Also in the parameters, we can find sometimes the recommended operated temperature or maximum case temperature, so this kind of parameters, but much less of use from practical point of view. Okay, what are the main elements? What are the main options we have for dissipating the heat from our PCB board, and of course as well from our box, from our case. So we have we can use a heatsink, we can use a Peltier element, we can use fans for forcing airflow, and we can force the water or some other liquid to dissipate the heat from the device. So 4 elements, and let's analyze them. So first thing, heatsink. Heatsink is the metal element, so the element from the thermally conductive material. So usually it's aluminium because it's cheapest, and it's fairly cheap, maybe not cheapest, but it's fairly cheap, and it's conducting heat very well. So its heat conduction is very high, and as well it's mechanically strong, because we can construct from it very complex structures, and they will still be stiff and sturdy. The idea about the heatsink is that we increase with the heatsink, we are to increase the area of the power dissipation. If the larger the area, the larger radiation, conduction, and convection can happen, increasing the power, the heat transfer, the heat dissipation. The heatsink itself may work in a conduction with the forced airflow, but also just a simple natural airflow may be used. It really depends on our need. As you can imagine, forced airflow delivers better results, but we'll talk about it in some time. The important thing about the heatsink is the very good connection to the silicon itself, so very effective connection to the silicon itself. This usually requires special thermal path for connecting the heatsink, but even if your chip is not having a thermal path, even just in a normal plain case, even in this situation, adding a heatsink to such a device using some thermal conductive paste between the device and the heatsink is necessary then. But even without a thermal path, the heatsink would pump out the heat, would help to pump out the heat out of the chip itself. But of course, the best way is when we have a special thermal path which has a very good conductivity of the heat from the silicon die itself. In case of heat sinks, we've got we've got a couple of categories of the heat sinks, and the major category and the simplest one can be classified or can be named as the passive category. The passive category, with the passive category, we mentioned about the passive category when the elements are just plain mechanical constructions. So usually it's a metal plate or some metal shaped element that's conducting heat and spreading the heat from our device, from our silicon on the larger area, allowing for the radiation conduction and convection to work effectively. Of course, that's natural, which means that for low power density applications, so when we have a lot of space possible, or there's a lot of volume possible, not even space, but a lot of volume available for the heatsink itself, and or when small powers can be dissipated, when we don't need to dissipate large amounts of heat. Then if we add the airflow, so if we force an airflow, to this passive heatsink, the metal plate or whatever we use, and we talk about the semi-active or active cooling, because they are the categories are very similar. So the situations where we don't leave everything to the natural airflow, but we force the airflow. Why? With constant airflow, we can classify the device for semi-active. With variable airflow, so because there are also systems where the airflow changes with the temperature, with the needs, with the requirements, or because sometimes we need, like we have in computers, for example. Take a look. In computers, quite often we have a fan that is quiet if nothing happens, or if the PC is in idle, but when the PC starts to, when we start to use the computer for heavy calculations, then the airflow starts to increase, and that's what we call by active category. That we classify to active category of heat sinking. Then we may have this liquid cooling. So instead of dissipating the heat to the air, we can try to dissipate it to liquid. And the last category of the heat sinks is the phase change. What is meant by phase change? Well, we talk about it. So if the material evaporates, so usually it's about having the liquid that does evaporate because of the evaporation. So the phase change, this is very effective. The problem is that we need to compress again the vapors during compression. So this is kind of phase change cooling. With phase change cooling, we meet at everyday basis in fridges. That's actually the phase change cooling. In electronic devices, in small electronic devices, the phase change cooling is quite rare, although liquid cooling isn't, because with liquid cooling, for example, Microsoft Surfaces, they do have liquid cooling inside, so of the processors, and the chips, like bridges, they are liquid cooled as far as I know. Phase change cooling is much more rare because it's expensive actually, and the components are quite large. So unless we need really to dissipate a lot of heat, we usually stay with passive, semi-active, or active in the active categories. In case of the passive category, the major element of the major importance is the heatsink itself. So the larger the area in general, because that's here, the larger the area of the heatsink, the better. Of course, the shape is as well important, but the larger the area, the better. With large areas of the wings of the heatsink, we can stay with passive cooling. We don't need. We can stay with natural airflow. When we want to have a smaller heatsink with lower area of the wings, then usually we would need to use some active or semi-active, at least, cooling system, so fan in general. But the heatsink itself, there is a variety in the market. So from the very tiny ones, like few having the sizes of a few cubic millimeters, having the volume of a few cubic millimeters, to very large ones having the volumes of maybe not meters, but cubic, tens of cubic centimeters. And there are different techniques behind producing of this kind of heat sinks, of heat sinks themselves. So 4 major categories against the production technology. So technique 1 has stamped heat sinks, technique 2 extruded, technique 3 bonded fin, and technique 4 casted heat sinks. The stamped is the simplest one, yet the least effective. So it's the cheapest technique, but the least effective. Some photos. So stamped heat sink, as you can see in this kind of heat sinks, it's just one sheet of metal, usually aluminum as mentioned, sometimes steel, but only for special constructions. The aluminum is mechanically special construction. Steel is better mechanically, but worse from a thermal point of view, and as well much heavier, which is something as well not really welcomed. Anyway, this kind of stamped heat sink is very simple to produce, very cheap, but quite not very optimal from thermal point of view, because the area general thing is that there is limitations in the how we can produce it. So the number of wings and the area of the total area of such heat sink is limited. So price good, capabilities, possibilities not really special. So only for small and not very demanding applications. Then we have the extruded version of the heat sink. Extruded means that we have the device have some sort of symmetry usually, but it can have, and usually does have those extruded heat sinks. They do have much better shape than before. So again, there are certain limitations because they are extruded. They are aluminum by default. This extruded heat sinks, they are from aluminum, so they are extruded. They are available as bars, as long bars that they are just cut into shorter elements, and this is one of the limitations of this technique, that we can't have simply done or simply available. There are no heat sinks of this extruded version of any shape, so of any size. So we have to decide about we have to adapt to what we have, what's available on the market. So we have to choose the element or the type of the heatsink that's available on the market, and we have to adapt the existing heatsink to our PCB and to our devices. But the good thing about these heatsinks is that they are the price is still nice, so they are more expensive than the stamped heatsinks, but they do offer much better parameters. Take a look at the area, for example, here, the area, or here, the area of the wings is much higher, meaning that we can dissipate the much more heat from those extruded heat sinks, both with natural airflow and with forced airflow. So these extruded heat sinks are the very good choice usually for the application. So we have some limits about the shape and size, so we can't find usually that small because these are much smaller. That's in a scale, it's about 2 centimeters by 2 centimeters, while here the scale is about 5 centimeters by 10 centimeters, something like this. So they are much larger, but they are usually aluminum, and they do offer very nice parameters. So here is an example of the bar, and you have to cut in many directions and adapt to your circuit. Then more complex, way more complex and way more expensive is a bonded fin heatsink, and this seems to be the same, right? Take a look. What's the difference here and here? Actually, the difference is this. So the difference in general is the area of those wings, because we are not able with extrusion technique to make those wings are as thin as those ones. But take a look, those wings are much higher than those wings here. Because with extrusion technique, of course, we are limited with the height, and we are as well limited with the distance between the wings themselves. So the distance here. With bonded fin heat sinks, we can place the plates here much closer to each other, offering even more space, even more area, even more dissipation area. So this bonded fin heatsink works much better. It's much more effective from the volume than, because of those two facts, than any extruded heatsink. So the bonded fin. The problem is with bonded fin, unfortunately, the price. It's usually heavier, significantly heavier, and usually, but the price, because weight is just part of the problem, a small one, but much more important is the cost, because we need to. The technique is to not just to make a simple extrusion out of the aluminium, melted aluminium. But here we have to make some machining and gluing of the elements and so on. So the bonded fin is expensive and it's problematic. In some situations, we have 4 categories. Some situations, the 4th category is found or is used. These are so-called casted heat sinks. Casted heat sinks it's a technique, of course, different from the other ones, but the casted heat sinks, the good thing about them is that they are available in various sizes and various shapes. And we have really plenty of various casted heat sinks around. Here is on this photo an example of quite a large case where the heatsink, the whole case is casted, and the heatsink is integrated into this casted case. But on the market, they are casted heatsinks as well available in much smaller sizes and dedicated to be heatsinks itself, not integrated with the case. Casted heatsinks against the extruded ones, they have the difference that more shapes are available, because with extruded, it's usually, with extrusion, usually we have a bar that we cut here, sometimes also cut here, and then we cut out some part of it, which means that we need some machining. So the extruded material is very cheap, but we need additionally to machine it. In case of the casted heatsink, we have quite often, like with the stamped versions, available heatsinks already in the shape that we can use. So advantages, the price, so the effectiveness of heat dissipation similar to the casted aluminium, of course lower than the bonded fin heatsink, but the prices as well much lower. For the more complex operating principles, because those heatsinks were for passive active and semi-active cooling. But of course, for liquid cooling, there are also special heatsinks available, usually custom designed, because the liquid, using liquid or changing phase is very problematic from practical point of view and very expensive in electronic devices. So usually those liquid and phase changing heatsinks are custom designed, and they are not that available in real in as components for real applications, as components for of the shelf, so that we can take and implement into our device. The heat sinks, they assemble. The next thing that we should think about when using the heat sinks is how to attach them to our board. Naturally, the simplest way to do it is to use the adhesive and to glue it. So there are special thermal adhesives that you can use, thermally conductive adhesives. And the simplest way to do it is frankly to use the epoxy glue. The epoxy glue, a thin layer of epoxy glue works. So in my opinion, it works fairly effective. But to be frank, the use of adhesive is the worst method. Here of the three ones here, because we have the pins, hooks, and adhesive method. The adhesive method, because with adhesive method we are, so if you try to use it, so small warning from me, from the perspective of time, with the adhesive method, we have to, it means that we are gluing some mechanical element, heavy element to a chip. Even if the chip is in a QFP board, QFP, I don't know, 80 or 128, or BGA in a large case with many connectors and with many balls. Still, we are loading our chip with heavy mechanical construction. And in real usage, where there will be some vibrations, this additional burden on the chip itself may easily lead to malfunctioning of this chip, or by breaking the connection between the pads and the PCB. That is one point of the problem. The second problem with the use of adhesive for gluing the heatsink is of course the dismantling of everything. Because if you can't take off the heatsink, how would you dismantle your device? How would you dismantle the broken chip, for example, without breaking the PCB, for example? So the adhesive, although seems the simplest solution, is really the worst one. So when we have the heatsink, we should use some mechanical mounts. So we should use some pins or some hooks, or some other mechanical screws, some other mechanical elements. So the heatsinks should be mounted mechanically. So really avoid in your designs using adhesives. This is the simplest way, the simplest method, but really the worst one, by far the worst one. So the heatsinks should be mounted mechanically to the PCB or to the shielding or to the box or wherever they are to be mounted, and they should just touch the cooled element through some thermal conductive material. In case of the heatsink, very important is the airflow. Very important role does it play. Here is some example of some comparison between the natural convection and forced convection. Here the natural convection, take a look, it's when there is a 1 watt to be dissipated, the temperature rise is to about 25 degrees. With 2 watts, the temperature rises 50 degrees of the device behind the above of the junction or the case of the device beyond the ambient temperature, and so on, so on. So it rises linearly with the dissipated power. In case of the forced convection, adding of certain airflow actually reduces the thermal resistance. Reducing thermal resistance means that, of course, the temperature will, if you increase the airflow, the temperature with the constant, having the constant power loss, the temperature of the case cooled of the case itself and the junction will drop. So the larger the airflow and the lower the thermal resistance, thus the lower the temperature of the junction and of the case itself, which is what we want. The problem is that we can't really give an exact numbers here because they do depend on the, for example, on the shape of the heatsink. So with the heatsinks of this shape, so with large area, even smaller flow would reduce the thermal resistance of RTH very significantly. But for such simple cases like this one, the same small airflow would reduce the thermal resistance also, but very slightly. So the exact numbers unfortunately have to be tested in the real device with real, or here is very nice extruded heatsink. So it really depends on the heatsink itself and on the devices that we call. Okay, that would be it for today, because it's already a break, so we haven't finished the subject, but we'll continue the elements of the thermal management. We'll talk about the Peltier element, very interesting elements in our toolkit for in the thermal management of electronic devices. But we'll talk about all this and more next week. So thank you for your attention today, and have a nice day. See you next time. Bye-bye.
Goodbye.
Goodbye.